will pick up that several questions, or the authors can answer later. Okay, let's go to the next one, Shinan.
Yeah, thank you. Hi, everyone. My name is Shinan. I'm a fifth-year PhD student from the University of Chicago. Today, I'm honored to present to AMIR, our system for active multimodal interaction recognition from video and network traffic in connected environments. This is a work jointly done with Ohio State University. We came from Noise Lab and Kai Data Group. Today, many people are using videos for activity recognition. At home, people deploy cameras for elder care, children care, or pet care. We also have indoor cameras for surveillance or home automation reasons. However, video classifiers can be brittle. They often suffer from statistical failures. This is because activities, environments, or users often have a very long tail. It's very hard for a video classifier to generalize across all the occasions. And also a fundamental requirement for video is that it requires line of sight. So occasions like occlusions, obstructions, different camera angles, or bad lighting, or affect the effectiveness of video classifiers. So we ask ourselves one question: how do we actually augment this powerful but brittle visual activity recognition with another alternative data source? As a networking researcher, we observed that in connected environments, for example, in smart homes, smart building, smart factory, the proliferation of network devices complements videos for such a recognition task. Let me show you an example. Here's me entering this IoT lab to open the door for a smart fridge. You can see on the right side, it generates a network traffic pattern, which is quite unique, and they highly correlate with each other. Even better, capturing network traffic does not require any specialized sensing hardware to be deployed. You can find a router at most of our households. It's a general purpose sensing hardware. And it is agnostic to the physical surroundings of the activity recognition objects and subjects. It provides us like a cyber perspective on the ongoing activities. It is very generalizable across environments. However, video relies on the physical characteristics of the actions, and it can generalize across devices. So they complement with each other. In order to investigate more, we collect our own data set and we open source it. It's about over 2,000 pairs of collections, and we test it across 7 different participants. We deploy router and stationary camera at home or in lab. And we collected 17 different activities across 5 representative devices. So here is the first result I find quite exciting. Indeed, network model is very reliable when physical arrangement, like physical surroundings, change. For example, if we are testing, training and testing at different environment, you can see that a video classifier might just cannot generalize in a new environment, and the F1 score degrade largely in this. But network models is more robust against such a change. Now that we established that, okay, these are perfect matches, and we want to combine these 2 modalities. But combining 2 existing models is still a non-trivial problem, especially when there are a lot of powerful pre-trained video models out there already. We want to leverage their capacities, and how do we actually build a supporting system for it? It remains a question mark. You may think, okay, let's take the video features and take the network features, and we concatenate them together, do some feature fusion. However, this approach essentially needs you to retrain the whole model in order to intake this specific new feature. Even worse, to do such a retraining, you need all the paired collections to be all the samples to be paired collections, which is super costly when you think about the scale of this video model. Another baseline is to get the predictions from these two models separately and vote by their weights. However, for that, if one model fails, even in just several classes, the entire pipeline just fails. A smarter approach is to take the prediction vectors of these two models and combine them as the input of a third model, a stacking model. This would require some paired collections in order to train this calibrated model. So we want to take this step further, and we want to collect the least possible paired observations. That's why we designed AMIR, this framework. The idea is basically that paired collections are most valuable in classes where both models are uncertain about their predictions. So for example, here we have two models, and they have their own output vectors. We need a validation set, but this validation set can come from any environment because the uncertainty can transfer across environments. For example, here we have class 1. There is these paired collections, and we pass it through these two models. Then we get this uncertainty on this class, and we synthesize it as one entry of the uncertainty value. We do this again for class 2, pass it through, get the uncertainty of this prediction, and synthesize it. We do it again for class 3. Now we get this uncertainty vector. Based on this uncertainty vector, it basically guides us on what exact distribution we want to collect on these paired examples. Yeah, for example, the most uncertain classes are collected the most. It appears that AMIR is a very efficient framework compared to baselines, to other prioritization approach. We can collect 120 pairs less than random selections, and we can saturate the F1 score 5% higher than random collections. Yeah. So the takeaways for this work is basically, network traffic is actually quite reliable when physical surroundings change. And stacking is a way to go for efficient combinations of two existing models. AMIR helps to combine two pre-trained models with fewer paired samples and achieves better performance. We open source all the data sets, the features, models. Yeah, feel free to scan the QR code and access them. And I'm happy to take any questions. Thank you.
Thank you, Shinan. So if you have a question, then please raise your hand or come to this microphone, please. You can keep changing. Nothing? Okay, I have one question.
Sure.
Okay, so you merged, integrated two methods, but maybe I think that you have some pros and cons, some in case to case, right?
Yeah.
So can you say something about this one?
Yeah, so if we have paired examples for all of these modalities, the best way is definitely training from scratch. Then you can get a higher accuracy. But the case is that collection is very costly, especially when you are deploying in a new environment. You probably don't have all the infrastructure or all the human hour to help you to do that. So that's why we developed AMIR, just to facilitate this whole collection process. We can achieve a good result, and also sometimes even better than training from scratch. So yeah, I think that's basically how we're gonna use it. Yeah, thank you.
Yeah, thank you. I meant that the case by case means that that in this case it is network is more stronger to predict than in that case. Okay, but we can talk later.
We can talk about
yeah. Thank you very much. Okay, let's thank the speaker again. And the next one is presented by the second author, Yu Guan. Okay, please go ahead.
Okay, thank you.